aromatic, anti-aromatic, and non-aromatic compounds. Aromatic compounds must 1. Obey Hooke's rule. Hooke's rule states that the number of pi electrons N, capital N, in aromatic compound equals to 4n plus 2, where n is an integer. Integer equals to positive whole number, that's a plus number, or negative whole number, that's a minus number, or 0. In this case, it is the positive whole number and 0 that matters here, where n can be 0 or n can be 1, 2, 3, 4, 5, and so on. Number 2, to be aromatic compound, the carbon in the aromatic compound are sp2 hybridized, meaning the s orbital will have 1 electron for bonding, the px orbital will have 1 electron, and the py orbital will have 1 electron for bonding. And because we're having 1s, 2 p's, that's why we call it sp2. And therefore, the s and the p's are on the same energy level. Because they have the same energy level, we call that degenerate. Degenerate means they have the same energy level. To be aromatic, you must have, or you must be cyclic, a ring of atoms, or they must be planar, all atoms in the same plane. To be aromatic, they must have conjugated pi system. A conjugated pi system is alternating double single bonds. Example of aromatic are A. Benzene, that's a pi bond, single bond. A pi bond has 2 pi electrons. So a pi bond equals to 2 pi electrons. And in this case, we have sigma pi. So that's 2 pi electron. 2 pi electron making 4. Another 2 pi electron. That's 6 pi electron. That obeys Hooke's rule. In Hooke's rule is 2, 6, 10, 14, and so on. We've got 6 here. So that's 6 pi electron. That obeys Hooke's rule. Example B is naphthalene. It's got 1, 2, 3, 4, 5. That's 2 times 5, that's 10. That's 2 pi electrons, 2 pi electrons, 2 pi electrons, 2 pi electrons, 2 pi electrons. That's 10 pi electrons. That obeys Hooke's, and that's 10 pi electrons. And its conjugated system, double, single, double, single, double, single. That's conjugated system, fully conjugated. Likewise, each carbon is sp2, 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 sp2. Each carbon is involved with a double bond. If you have a single bond, that's sp3, and that's tetrahedral. If you have a double bond, that's sp2, and that's planar. And if you have a triple bond, that's sp, that's linear and planar. So this is sp2, sp2, they're all sp2, and therefore naphthalene is also aromatic. Example C is anthracene. It has 14 pi electron system. It is also conjugated, double, single, double, single, double, single. And sp2 hybridization, you can see 2 electrons there, 2, 2, 2, 2, 2, 2, making 14 pi electrons. This is p orbital with 1 electron. This is p orbital with 1 electron. And when they sideways overlap like that, they form a pi bond. This is sideways overlap, and that forms a pi bond. These are the 2 pi electrons in a pi bond. A single pi bond has 2 pi electrons. This is sp2 hybridized system. Carbon, double bond, carbon, then carbon, single bond, carbon, double bond, single bond, and those are the hydrogen here. So this one here is sigma, and that's pi. This is sigma, and pi. Sigma, sigma, and pi. Sigma. So these ones are sigma. In the middle, there's sigma bond, that's sigma bond, sigma bond. The pi bond are between these systems here. So this is the double bond you're seeing now, and This is the double bond you're seeing over there, and this is the double bond you're forming there. So the sideway overlap, the sideway overlap, and the sideway overlap. So that's a pi, sigma, 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 pi, sigma, and sigma. So you can see the 2 electrons in a pi. 1, 2. 2 electrons in a single double bond. 2 electrons in a single double bond. So altogether, for benzene, the structure is benzene, C6, H6, and there are 2 plus 2 plus 2, 6 pi electron system. So that would be 6 pi electrons. And that obeys Hercules' rule, which is 2, 6, 10, 14. The difference between them is 4. 4, 4, 4. And it goes on. And that is Hercules' rule. And that obeys Hercules' rule because it's got 6 pi electrons. Therefore, this is aromatic compound. Let's look at an example of aromatic ion. Ion means it's got a charge, positive or negative. We're looking at a negative, which is cation. Here is carbon, 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 and this is sp2 hybridization. This is 2 electron. We can call that a pi system because a pi system has 2 electrons. So that's 2 electron there, 2 electron. So that's 2 plus that 2, making 6 pi electrons. This is how you draw it. You put the 2 electrons there, and that's a negative charge because it's got negative charge. You put the 2 electrons there, one on top, one below. Here is 1 because you need 1 from there to make the 2. So that will form a bond between these 2. And this is the double bond here. As you can see, that is the double bond, and here is the double bond. So let's count 1, 2, 3, 4, 5, 6. So this is a 6 pi electron. 6 pi electrons. That obeys Hercules' rule, which is 2, 6, 10, a difference of 4, 14, 18, and so on. So because it's got 6, that means it's got 6 pi electrons. That is also aromatic. So that compound is aromatic because this one can form a double bond here, or it can form a double bond and that can go over to there and that can go over there. That's why it's aromatic. Now let's look at anti-aromatic compound. For anti-aromatic, the number of pi electrons n equals 4n, where n equals to 0, capital N will be 0. When n equals to 1, capital N will be 4 pi electrons. When n equals to 2, capital N will be 8 pi electrons. When n equals to 3, that will be 12 pi electrons. When n equals to 4, that will be 16 equal to 0. If number of pi electrons equal to 0, 4, 8, 12, 16, and so on, then it does not obey Hercules' rule. It is anti-aromatic. Let's look at non-aromatic compound. If a compound does not have a continuous ring of conjugated pi system in a planar conformation, then it is non-aromatic. Hercules' rule is a useful first step in evaluating the aromaticity. Planar compound is not always reliable. Heterocyclic aromatic compound. Compounds with elements other than carbon in the ring can also be aromatic if they obey the criteria for aromaticity. Here's an example of heterocyclic. The cyclic indicating it's a closed ring, and the hetero means it's non-carbon. That's carbon and that's non-carbon. And we have drawn that in the structure showing the p orbital. So that's a p orbital. And we've got the 2 lone pairs of electrons. We can only use one and ignore the second one. So we ignore the second one and we only use 1 lone pair. So that's a 1 lone pair filling that p orbital. And this one has 1 p orbital with 1 electron, that carbon. This carbon has 1 p orbital with 1 electron, and they will form a bond. That's the double bond. Likewise, these 2 carbon will form a double bond here, and that's the double bond. So if we count this bond pi electrons, 1, 2, 3, 4, 5, 6. That would be a pi electron now because it's 2 of them. So this one has 6 pi electrons and it is aromatic compound. Exercise. Determine if aromatic or not. Pause, do the question, and then check the answer. Okay, let's check the answer for this one. You got 2 lone pairs here. Ignore one of them. So if I use that lone pair, well, you go 2, 4, 6. That's 6 pi electron. So that will be his Hooke's rule. And you can demonstrate these 2 lone pair can form a pi bond here by moving the arrow. So if I move the arrow from that can become a double bond, and this double bond we move there to become a double, and this will become single, and then when that becomes a double, this one we move back to there. So that's how that move around from this relationship. That's how it can form the conjugated pi system that move around. So that is what we called the aromatic. So that's aromatic. Number 2, well, you got a conjugated pi system here, but not here. This is sp3, that's sp2, sp2, sp2. So it's not fully conjugated, it's not aromatic. Secondly, you can count how many pi electrons here. That's 2, 4. And if you're 4 pi electrons, that's anti-aromatic. So number 2 is not aromatic. Question number 3. This has 2 here, and that obey Hooke's rule because that's 2. And that one can form a double bond here, and this double bond can go back to where it comes from. So there's a conjugated pi system, and this one obeys Hooke's rule because you go 2 pi electron there. So that is aromatic. Question 4. We've got the 2 electron there. So we got 2, 4, 6. That's automatically aromatic because it obeys Hooke's rule, and we just ignore that one. And so we can get the conjugated pi system, double, single, double, single, double. So that is aromatic. Question 5. Again, we have a double, double there, double, single, double. And we've got the 2 electron there. So we cannot ignore that because we haven't got like that. We can ignore 1, but here we've only got 2 electrons here. So that 2 electron can represent a pi electron. So that's making it 6. Because that's 2, 4, 6. Again, that's also conjugated because double, single, double. And that will make a double there, or that will make a double there. So this is obeying Hooke's rule because 2, 4, 6. That is aromatic. Question 6. We've got 2, 4. You have to ignore that one. 6, 8. 8 is 4N, anti-aromatic. So it's not aromatic. Question 7. We've got 2, 4. If you're 4, you're not aromatic. Even though it's conjugated, double, single, it's not aromatic. Again, sp2, 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 but it's still not aromatic because it does not obey Hooke's rule. Hooke's rule is 2, 6, 10, 14, and so on. We've got 0, 4. We've got 4 here. That's anti-aromatic, so not aromatic. Number 8. We've got 2 here. Ignore that one. So that's 2, 4, 6. That's aromatic. Number 9. This is not aromatic. We've got 2. That's Hooke's rule. That's good, but it's not conjugated. Unlike here, double, single, double, that's conjugated, plus that one to mix the conjugation, and this one has no conjugated system, therefore it's not aromatic. Not aromatic. Number 10, that is positive, we cancel the negative, so you just go 1 electron there. But you got 2, 4, 6, and it's conjugated, that's aromatic. So how many did you get right out of 10? If not sure, try it again.